Good morning. We're going to be doing some more vocabulary this week. This will be dealing with atoms, continuing with what we're talking about with atoms, but speak more about how atoms can now bond together to make compounds. And the first definition is one that we've talked about before, which is valence electrons. These are the electrons in the very outermost layer. We have the different layers that surround the nucleus, different energy levels. They have higher energy as we go up. And that very last layer, whatever electrons are in that very last layer, are the valence electrons. And these are the ones that really determine how an atom will react with other atoms. Will they form compounds or not? So if you have a picture of an atom, a Bohr diagram, look for the ones that are in the outer layer. This one, for example, has 3, 4, 5, 6, 7, 8 valence electrons. This is a noble gas. And I can tell that because 8 is kind of the magic number for these things. That's the number they want to get to. Most atoms don't have that. So anytime you have a drawing, just look and see those two there. So this is in group 2. This could be calcium or magnesium or something. Now, how can you tell? How could I tell that it's in group 2? Well, that's a nice thing about the periodic table. If you look at the periodic table, there's certain columns that will tell you how many valence electrons they are, because having a certain number of valence electrons gives you certain properties. Everything in group 1 has 1 valence electron. And that's why these metals, lithium, sodium, potassium, rubidium, and cesium, are extremely reactive. They're trying to get rid of that particular valence electron. If you look in group 7, like fluorine and chlorine, very reactive, poisonous, because they have 7, they want to get to 8. And lastly, if you look at the last group, they have 8 valence electrons, all of them. Those are the noble gases. One exception, helium has 2, filling up that level. 8 is a magic number because that kind of fills the column, that fills that orbit and makes it stable. No more need to go in. So having that number is what makes you the way you are. We'll be talking a lot about valence electrons when we get to how atoms bond together. Our next word is reactivity. When something reacts, it can change into something else. This is the ability of an atom to undergo some kind of chemical reaction. So reactivity is the ability to have a reaction, to form maybe a new compound. And some atoms are extremely reactive, like potassium. Some, like magnesium, reactive, but not as reactive as potassium. There's no fire there. Zinc, even less reactive. And of course, the noble gases are absolutely not reactive. Here we see a number of different kinds of reactions from different substances. Some of them can be pretty spectacular, but all of these are reactive elements having a reaction. The oxidation number is something we're not going to spend a lot of time with, but this is for every atom, the oxidation number is the charge that an atom would have if it was an ion. So for metals, that would be how many electrons, how many valence electrons do they get rid of and become plus whatever. For nonmetals, they're gaining electrons and would become negative. Those numbers, the oxidation number, would be the same as in those ions. And you can see, again, just like in calculating how many valence electrons there are, we can calculate the number of the oxidation number for a particular column. That's what makes the periodic table so powerful. It gives you the properties of elements that are in a specific column. Even though they're different elements, they're in what we call a family, because like family, they have certain properties in common with each other. And if you have the table, you can use that to really determine what an element is likely to do. An ion is when an atom is no longer neutral. It has either gained electrons to become stable or lost electrons to become stable. If they lose electrons, the atom will become positively charged. And if an atom gains electrons, they will be negatively charged. So usually when we have an atom, we say it's a neutral atom. They have equal numbers of protons and electrons. But in ions, that's not the case. In ions, they are going to gain or lose electrons and then become a charge. Losing electrons becomes a positive cation, and gaining electrons becomes a negative anion. We can see here the result of this. Sodium and chlorine. Sodium is throwing away one of its electrons, and giving it to the chlorine, which has 7 and wants 8. Now, as a result of this, ultimately, we're going to have bonding because now we've created an ion that is positive and an ion that is negative. And that is, in fact, our next vocabulary word, ionic bonds. Ionic bonds are when ions, positive and negative, come together. One atom loses an electron, becomes positive. Another one gains electrons and becomes negative. And we know that opposite charges attract. So this is what happens when you have a metal element, atom, that throws away electrons, meets up with a nonmetal that gains electrons. Metals and nonmetals together will pass their electrons back and forth, and then we get a positive and negative ion, which will then be attracted to each other. And a good example of this is salt, sodium chloride. Sodium became positive, chlorine became negative, and we get this bonding, as we see here in this illustration. What can you say about ionic bonds? They have certain properties, and anytime you think of an ionic bond, think of salt. Whatever's true about salt would be true about ionic bonds. It's an excellent example to use when you're thinking about ionic bonding. They are solids at room temperature. They have a very high melting point, really hard to melt salt. If you dissolve them in water, they will conduct electricity very well, or if you melt them, which is hard to do because they have that high melting point. And they are very soluble in water, but not so soluble in like oil, an organic solid. We have various illustrations of what this would look like. Here's sodium fluoride. The sodium gives an electron to the fluorine, and sodium chloride, same thing. Once they do that, the sodium becomes positive, the fluorine becomes negative, and they are attracted to each other in a very strong ionic bond. A covalent bond is different from an ionic bond. For one thing, it doesn't take place between a metal and a nonmetal. It's between two nonmetals. For example, hydrogen and oxygen. And here, neither one wants to give away any of its electrons. They both need electrons, so they share them. The hydrogen, which would like to have a full level of 2 electrons in that first energy level, shares one of oxygen's electrons and shares its own electron with oxygen. And so as a result, we have H2O, where both of them get what they want. Now, this is not going to be as strong a bond as the ionic bond is. They can be solids, liquids, or gases, but they have a low melting and boiling point. And they do not conduct electricity all that well. They are not terribly soluble in water, but they would be soluble in like oils. Here you can see the different electrons sort of just being passed back and forth. So we've had metals and nonmetals and 2 nonmetals. What about if 2 metals come together? Well, reasonably enough, it's called a metallic bond. And metals don't hold on to their electrons very much. So the expression that's often used to describe a metallic bond is that the metal atoms are floating in a sea of electrons. The electrons just sort of go from one to the other. And this actually explains a lot of things about metals, like why they conduct electricity so well and why metals will bend. It's like the atoms are kind of sliding through this sea of electrons. This can be illustrated in a number of different ways. Polyatomic ions. Now, poly means many, and ions are charged atoms. Well, here, a polyatomic ion is made up of more than one atom. So it's a group of atoms that are bonded together covalently and will have a positive or a negative charge overall. And what makes them significant is this whole group, like here's NO3, that's going to travel together as one group. The oxygens and nitrogens aren't going to break apart when we do compounds. So they will actually travel together and almost have to be treated as though they are a single element. There's a number of them. They have a table that goes with them. They often end in ATE, so chromate, bisulfate, nitrate. You would just look from here and you can see the charges. And that's going to be important when we discuss how different polyatomic ions and elements will combine together. Diatomic molecules, di means two. So these are atoms that will join to like themselves. Oxygen. When you breathe oxygen, you're actually breathing O2. Two oxygen atoms have joined together and formed a molecule of O2. There's a number that do this. Nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, and iodine are the ones that do this. On the periodic table, it kind of looks like a 7. And they actually have a good little jingle that goes this: have no fear of ice cold beer. If you can remember that, have no fear of ice cold beer, that gives you the first letter of the atoms that tend to do this. And lastly, chemical formula. This would be like H2O. It's the representation of the molecule. So H2O tells me I've got 2 hydrogens combining with 1 oxygen to form a molecule of water. It gives you the formula exactly how many atoms there are in the compound. Here's sugar, C12H22O11. I mean, that's telling me that I've got 12 carbons, 22 hydrogens, 11 oxygens. It doesn't tell me the shape. It doesn't tell me exactly how they are bonded together, but it gives me at least the formula of how many I need in each one of these. Well, this is all going to become very important this week when we start figuring out about bonds and how things can come together and break apart and what you can expect to have happen when you mix certain atoms together. So you take care. I'll talk to you soon.